Hello, welcome to my Ames, Iowa housing price machine learning predictions regression model, which is my capstone project of a regression model machine learning unit. My name is Mike Struess. I'm a data analyst from Milwaukee. What are the aims of this data set? Pun intended. The purpose is to predict house prices in Ames, Iowa using various dataset features. Identify factors influencing housing prices, for example, the quality of materials, the neighborhood, and property features. Some of my project goals were to identify key features affecting house prices and to develop an accurate predictive model for real estate valuation. On the right side of the screen, you'll see the distribution of housing prices in Ames, Iowa in 1995. You'll note there's a high concentration in the low to mid 100,000s with a longer tail on the right side of the distribution. Here's the size of the data set when I received it. There were two data sets. One was the test data set, which was 878 by 80, and one was the train data set 2051-81. The reason the train data set has one more column is because it contains the sale price. Uh, of of these 80 variables, about 40 of them were categorical, and the other half were already numerical, some of them continuous, some of them discrete. So you'll see how I dealt with those in an upcoming slide. So all of the variables, or one of the first things I checked rather was checking for nulls. Most of the nulls, especially if they were categorical, were either NA or none compared to other rows where the house didn't have that feature. So I had to be careful to match it to what the non-type was for that category. I also filled some other cells with measures of central tendency. I actually made the mistake at first of using the mean of the whole data set to fill the gaps. I learned later not to do that because that bleeds information from the train data set into the test data set. So I went back and fixed that. I also used one-hot encoding for all categorical uh, features. If you don't know what one-hot encoding is, it basically makes a new category for every subtype of that categorical variable. Say you had M&Ms and they were red, blue, and green. Well, it'll make a category for M&M red, M&M green, M&M blue, and then if that particular M&M was red, there'd be a 1 in that row. If it was blue, there'd be a 1 in that row. And if it doesn't apply to that row, it gets a 0. Here's a slightly bigger graphic of the one I showed you earlier. I did consider the outliers. You'll notice there's not a ton of houses above 300,000. So I examined those houses above 300,000 and looked at the common features that are associated with a more expensive house, neighborhood, square footage, number of bedrooms, number of bathrooms, and I didn't see any oddities in those outliers. They seem to accurately reflect the value of the house. So I chose to keep them in the data set. Then I started testing out features. I tested the categories against sale price and found some of the categories that had the highest correlation. The one that had the highest correlation that I had a love-hate relationship with through this project was overall quality, because it has a very high correlation with sale price, but I learned later there's something better than overall quality. How could that be if it's the highest correlation? More on that later. So these variables are basically what I used for my first machine learning model to predict this data set. Most of these are measures of positive value. If you look at the bar chart on the left, that's a measure of what the value add is or what the value subtraction is for per 1 unit of the variable. For example, exterior quality 4, I believe, was the highest quality of exterior rating. So if it had a 1 in that category, this is saying it has about a $9,000 or $10,000 value add for having that binary 1 in that category. So basically all of the high correlations you saw on the previous screen, some of these deal with curb appeal, kitchen quality. I only included the highest quality kitchens, which were highly correlated with a higher sale price. You'll see me rethink that later in this progression. And I also included higher quality basements. Uh, my logic at the time is if you're shopping for a new house, you would only consider the basement as a value add if it was like a nice basement. If it was an unfinished basement or a poorly finished basement, you might not value that much into how much you want the house. So I kind of looked at this at first as what are the things that make you want to drive up the price? One of the correlations you saw on the previous screen that I didn't put in this first model and only ended up putting in one of the models throughout this whole thing was overall quality. I saw a lot of these quality measures had a high correlation with overall quality. So to cut out multicollinearity, I removed overall quality in favor of more specific quality measures. This achieved a RMSE of 34,500-ish and put me in first place in the competition. Next, I did the Rooms Plus model. As someone who's shopped for a number of houses in my day, I've noticed that houses with more rooms, more bedrooms, more bathrooms usually have a higher selling price. So I scoured the features for different room options. So this model has living area, garage spaces, lot frontage, year built. But here's this third bullet. Here are the rooms I added. Full and half bathrooms, a basement full bathroom, and bedroom counts. Interestingly, half bath, bedrooms above ground, and full bath were all negative correlations. One thing I've found interesting about machine learning is you never quite know what the model is going to put the positive value on and negative value on, and sometimes it's counterintuitive. I also excluded total rooms above ground to avoid redundancy. That was a metric I thought about using, but there's more specific measures of what kind of rooms it has. This improved my score by about 1,700, having information about the rooms. This next model is simply explained as I added all the neighborhoods to the machine learning model. On the left side of the screen, you'll see the correlation measures of neighborhood and sale price. I toyed around with only using the best and worst neighborhoods in the model, but I found it performed best when I included all the neighborhoods. So in any of the future models where I say I use the neighborhoods, I used all of them. And this improved my score by 1,000. Uh, as I continue to evaluate my progress, I noticed most of the variables and features that I used were positive, with the exception of a few neighborhoods. So I look for things that might indicate some deductions that might be given to a house when it's assessed, including the lower quality ratings for basement, exterior, and kitchen. I added features of basement condition, exterior condition, and functional. The functional ones seem to be like how turnkey ready is the house? Is it ready to be used, or is there a whole bunch of stuff that needs to be fixed? Which is a thing that could greatly add value to the house and be a huge red flag for a house that would drive down its price. I kept in key features that seem to have good predictive value in my previous models. And combining these positive and negative features, I dropped my score by another 520. After this model, I had a few unsuccessful models. I tried a kitchen sink model, which basically I took every single feature besides the sale price and trained the model on those 380-ish columns. And at that point, it missed my high score by 8,000. So some overfitting going on there, I would presume. Overall quality, I tried a model where I took out all the specific quality conditions and just replaced it with overall quality. And while that still achieved a decent score, it was not my top performing model. So one thing I learned overall as I did this is specific measures of quality are better than generic measures of quality. And I took a model where I restored high null columns that I deleted earlier. They had to deal with alleys, fencing, and miscellaneous features. I figured if they were maybe special things that 300 of the houses had that the other ones didn't have, maybe that they were things that would drive up the price of those 300-ish homes or lower those homes, or train the model if it has one of these rare things to have it raise or lower the price. While that received a decent score, it still wasn't my best score. These last couple are some of my best. This one is called the Last Touched model. I engineered a column called Last Touched, which took the newer year of when the house was built or when the house was remodeled. So if the house was built in 1960 and there wasn't any records of being it upkept since 1960, 1960 would be its last touched score. But if a house was built in 1960 and it was recently remodeled in 2017, then 2017 would be the value in the last touched model. I searched out a few more negative variables or negative leaning variables that I hadn't included in my model. I think like a C block foundation was one of them, for example. This reached a new low score or high score, depending how you look at it, of 30,730. I had a featured engineering model where I just started imagining what type of other variables could be added. The most helpful of them was bed size. I took the square footage of the house and I divided it by the number of bedrooms and called that bed size. Obviously, that's not the average size of the bedrooms because there's other rooms in the house besides bedrooms. But I gave the model a general idea of like how spacious could the bedrooms in this house be? Or is this like a 4 bedroom, 2 bathroom house, but like all of those bedrooms are super tiny, I think is what it was teaching the model. I also did a age remodel feature, which had too much similarity to my last touched model that it didn't have much value add. But leaning on bed size, I think that took about an extra 1,000 off. I almost quit there. I slept on it, and the next day I was like, I gotta break past 30,000. So I was racking my brain. So what did I learn from the models I did already? I learned that specificity is better than generalization. And I remembered learning earlier that in a regression models are really good with continuous numerical data. And that's something I don't think I put an emphasis on in my earlier models. So I went back to the data dictionary that came with this data set and I searched out, I control F the word continuous and read about every single continuous feature. And I added all the continuous features to my model first, ran it, and then gradually started adding back in the other things that seemed to be a positive addition to the model, kind of the best of the best plus more continuous features. I called this my more continuous variables model. This is the one that helped me break through 30,000. My main variables, these would be the continuous variables. Then I added back some quality measures, some specific quality measures about different quality measures of different parts of the house. The functional ratings 1 to 7. This was the metric that was kind of how turnkey ready is the house. Is there a lot to be fixed? Which would be a 1 if this was like, this place is going to be totally gutted. The foundation needs work. That would be a functional 1. If it was like this house was just flipped beautifully, or this is a brand new house, that might get a functional 7. I found that I had a high predictive quality, and I didn't include that till later models. Some nominal and ordinal one hot encoded features that I used earlier. I added and subtracted those, seeing which of those still had value. And then I asked the question, I put it into comments, are neighborhoods still important? I added the neighborhoods and that dropped off another few hundred, which helped me break the 30,000 variable or barrier, giving me an RMSE of 29,700-ish. On the right, you see my coefficients bar chart. Towards the top, you have things that gave the greatest value to the house predictions, and on the bottom, what took prices away from the prediction. I also made the point several times in my Jupyter notebook that sometimes in the middle, things like square footage seem like it's almost a 0, but square footage had a predictive measure of about $60-ish. So for every extra square foot, the house would be $60,000 more expensive. So while those seem like not to be huge coefficients, if it's a continuous variable that has hundreds, if not thousands of units, well, you multiply that, and sometimes those have a higher predictive quality than neighborhood, for example. On the Kaggle leaderboard, all of the ones that are on here would be the current high scores. I was only the second Coding Temple student to jump into this Kaggle competition. I got to see the person who came into it first. My teacher teased us that she'd seen someone get into the teens on this before, so that kind of drove me to strive for that. I struggled to get out of the 30,000s. I'm interested to come back later in the year and check to see what future students did or didn't pass my score and what they maybe used. Some other things that I learned: localized quality measures outperform universal measures of quality. Continuous numerical variables are better for prediction when possible. One-hot encoding variables for categorical data not captured by existing numerical features. In other words, continuous variables, great, but from your categorical variables, what part of the story or what part of the information about what you're predicting was not captured by the continuous variables? Those things you want to one-hot encode. I went a little crazy and one-hot encoded everything, which kind of made my data parsing a little more difficult. So in the future, I might only one-hot encode things when I want to use them. And last thing I learned: inventing new features from old ones can improve the model and be a fun process. It was fun kind of playing around with the features and see what new things I could come up with. So I look forward to doing that in future machine learning projects and real world examples. Well, thanks for watching my breakdown of my machine learning model for this data set of Ames, Iowa. I hoped you learned something about real estate data analytics. I learned a little bit about regression models in machine learning. If you'd like to reach out to me personally, my email is mike.struce@gmail. I'm located in Milwaukee, Wisconsin, looking for data analyst roles in Milwaukee or remote. You can also find me on LinkedIn. Thanks for watching.